So let's look at we're making our way to vectors and all that. But before that, let me introduce for you guys a little bit with the three-dimensional space here. Okay? So about contact getting to know three-dimensional space. Okay. Because yes, maybe somewhere here and there you learned that maybe a little bit here and there from your class before this class right here, but here we're gonna give a formal look at that. And then after that, when you're getting into vectors and all that, and after this quarter is being over, you guys go to your Calc 4 class, and it's going to be completely all 3D. Okay, so that's why let's now give a formal understanding of what 3D is all about. So back in your day, up to any lecture prior to this one right here, anytime you're looking at a graph, we think of two axes, right? So, and that's what we call 2D. Basically, one dimension is one axis here representing one dimension. Okay? So it's just a plane, anything graphing that we have done up to the point of that lecture right before this one, then a graph is just, see, there's an axis, the horizontal axis, and there's a vertical axis, right? And yes, we call that as a 2D axis. And the point here, the point there is represented by two components, only two components, right? And that's once again, that's why it's 2D, two components. So we represent by the horizontal coordinates and vertical coordinates, okay? And so each point has a pair of values, okay? Meaning the x and y, horizontally and vertically. And the origin is right at 0. Okay? So the story is done there, and from there it produces a graph and all that we've been learning since your very beginning algebra course up until this time, right before this point here. And now switching over to 3Ds, we have to make some adjustment. Think about the x and y plane that we've been working with so comfortably. Now we have to treat them as the floor. So you guys can imagine from anywhere you're sitting here, looking to the corner again. Look right into that corner. Then imagine this way, that going to your right-hand side, this way, to your left-hand side, is the x-axis. Okay? And then that edge right there, that's the y-axis. So the x and y plane now is going to become the floor. We're looking down on the floor. So your eyes are looking down on that. Am I making sense there? Okay, so now, and so we're going to have a third axis coming up from that, where we call it the z-axis. Sounds good? So just like when you're looking at that corner right there, so x-axis is here, y-axis is there, right? So now the z-axis is the one going up. And that's the positive direction. Okay? So positive direction on the axis here, positive direction on the y is there. So if you're going back into that way, those are the negatives. And if you go down below the floor, that's the negative on the z-axis. Sounds good with that? Okay? So imagine that floor, that corner of your room right there. So, as far as the picture, just like that. See, doesn't the corner of the room looks like that? Fair enough, right? And of course, I'm not the best artist, but I'm trying to make it as closely as possible. So our eye is looking down at that, right? The corner of the room is right there. X-axis, that's the positive x-axis, that's the positive y-axis. So z going positive, going up. That's the one. Right? And so, yes, going through the floor, that's the negative side of the x-axis, right? Going through, so now all of a sudden there's x, z here forms a wall, right? You got the floor here, and then this left wall right here is the x, z plane. You guys follow me? Okay. So right from there where you are, you're looking right at that corner again. This wall right here where the board is at, right? That's your x, z, x, z, I wrote x, y. Okay? That's the x and z plane there. It's a wall. Sounds good? And then, yes, there's y, z plane is right here. Okay? And then this plane right on the floor right there, yes, that's the traditional x, y plane that we used to know. We've got one floor and two walls that try to come down when we're looking right at that corner again. And these axes are supposedly perpendicular with each other. Okay?
So if it's going down, it's not like z, y, something like that?
What's that?
X, Y.
So this is XZ right here, this wall.
Yeah, I mean the right.
This one here is a YZ.
Yeah, and how about the X, Y thing?
And then the floor here is the XY plane.
Oh, the floor.
Yeah, the floor.
Oh.
Yeah, I'm trying to draw it, to put it on the floor, but yeah, I'm trying to stay away from that dotted line because the XY plane is the floor. All agree now? Okay. That's why I was saying earlier, try to trigger up your visualization skill right now. Okay? And so you downweight. So now, what's the convention for any point in space? So that was, a plane is a two-dimensional space. So now we've got a three-dimensional space right here. Right where I put the finger, the pencil tip right here, that tip is a point, right? It's a point in space out of infinitely many points around it. So that's where it's located right now, right? There's a coordinates relative to the x-axis. There's a coordinates relative up and down relative to the to the z-axis, right? And there's a coordinates that's relative to that y-axis right there. Okay? So in the way how I see it, the three axes, going like that, we pick the points, right? And you can just make your best out of that. Draw a line parallel to that. So that coordinate right there, so we got that point is x, y, and z. We stay convention to that. So the x-axis, y-axis, and the z-axis. Okay, so with that point is now no longer a pair, but now a triplets. Okay, it's a triplets. Okay. And so x coordinates is, think about, we make a projection. So right on that point, right? Think about the projection on the floor, on the xy floor. Then with that projection, right, the x-axis is about, the x coordinates is about there. So you got to think about the projection on the xy floor, and then from there we're going to put that, we're going to trace it back to the x-axis, and from that projection on the xy plane, then we're going to trace it back to the y-axis. And that's how I can see the x, y, and z coordinates of that particular point in space. Okay? So a little more formally now. It's time to let you guys know anyway. So a formal term for 2D, for two-dimensional space, like back in those days, right before this point, we call that as an R2. So this plane right here is called an R2 space right here. See, this plane is combining two dimensions, right? X dimension, the horizontal axis, and the horizontal axis and the vertical axis. And so we call it as the R2 space right here. Or now it's just the set of all x and y pairs, right? Satisfying that x and y, they're all in the real numbers. So this symbol here is the symbol for the real numbers right here, with superscript 2. It's indicating it's R2. It's the space of all the pairs, the collections of all the pairs in the R2 space, where each one of these x and y is in the real numbers. So that's back to the R2, and we're giving it a formal a formal term for that. So 3D world that we're about to step in right now, similar idea right here. Now we're calling that it's the R3 right there. Okay, it's the space R3. Okay, where it's a collection, it's a set of all triplets x, y, and z, where or such that, right? The vertical bar here is such that the x value, the y value, and the z value are all values from the real numbers. Okay? And that's how we formally define the R3 here as our three-dimensional space. Okay? We're talking about the physical space, right? Yes?
I'm just curious, is there like a fourth one too? A fourth dimensional space?
Yes. There will be. We will not formally talk about that until your days. If you're taking linear algebra, but there will be. But of course, when it goes beyond R3 then we won't be able to visualize anymore. But it's good that we can kind of mimic the idea here, kind of copy the idea how we work with those vectors, those points on the 3D space, and bring that to the hyperspace. We call it hyperspace because it's above what we can see. Okay? But but back to this, is there any questions so far? It's just a definition of what it means by the R3 space, right? And this is now the common name for, because instead of calling that 3D, this is for kilos, right? We call that, with more mathematical understanding, we call it, it's the R3 space. Okay? So easy enough so far, right? And I don't think you guys have any questions, because I can see that you guys are getting it. So let's now go a little deeper into this, okay? So now what we're specifically, and let's now leave the 2D space behind. We're kind of done with that. I mean, we're still looking back at that. But let's now pay more attention and focus more into the 2D space. And so I kind of used that word earlier. So think about the 3D space from here, x, y, z. If we pick a point, right? That point P right here with coordinates x, y, and z, whatever that is. So now I'm talking about specifically about the projection, okay? Because so now doesn't matter where your point is at in space, there will always be projection relative. I mean projection on the x, z wall. There's also projection on the YZ floor right there, right? And then there's also projection on the XY floor. I'm not talking about the projection, the shadow of that. See what I'm saying there? Okay? So think about this pencil tip right here. If there's a light right above it, then there's going to be some projection right down this floor right there. Okay? And so the easiest way, see, if this point, put it in your imagination. If we think about the projection of this point right on that X and Y floor, then yes, there will be X value, right? And there will be some Y value. But what's going to happen to the Z value here on that projection? So this is the projection, with that point on the XY floor. This is the projection, okay, of P. But then on the XY point, right? So of course, we're not artists here, so we're just making the best so that we can understand through the eyes that. But just imagine now, if this point is having that projection on the XY point here, then what's going to be the coordinates of that projection? XY, but then what? Now we all 3D space, right? So even if it lands on the XY plane, it's going to have a coordinates for the Z axis. Right? What Z axis? I mean, what coordinates is that? 0. Yes. So now you start seeing a rule right there. The projection on the XY, I mean any point in space, right? If you're taking the projection on the XY plane right here, so these two variables are here, but then the Z is absent, right? That means that we zero out that corresponding component. And that's how we create the projection. Okay? And so the same space again with the 3 axes. Oops, see, I'm still, the 2D's days are still with me. Okay, take a point, right? So now this point, coordinates x, y, z, and we take a projection right on that x, y, and x, z plane right here. What do you think it's going to look like? It's going to go straight in there, right? And at that point right there, yes, it's got x, it's got z coordinates, right? But what's going to be the y value? See, the name of the plane right here is the xz plane. That means these two variables are still there, right? But then the y, the name for the y variable is absent. So that means that that point right there, this projection here is going to have to be x, comma 0, and comma z. Right? The projection on whichever plane is going to have, is going to have to zero out the coordinates on whichever the missing variable right there. So the third case, okay, just like that. Once you already got a good hang of that. Right, so the point here, x, y, z, being components, right? Now, we're checking the projection. So let me draw. Because that point is looking a little too close to be on that wall itself already. So, checking that projection here, for example, right? There. That's the projection. And that's my short name of projection right there. So that projection, what's the coordinates? And this is the x, y, z. Okay. So this time the x-axis is missing, right? Because it's the y-z plane again. So it's a 0, comma y, comma z, y-z plane. Right? That's how you get the projection of these guys. Will you agree so far? Right. And so, in that way, once you understand about the idea of taking the projection, we can take advantage of that, and then it's getting a little old school with this technique right here. Because we start to have a lot of technology these days, but it's still good that we have this sense about observing 3D graphs again. Because think about this. Back in 2D day again, a graph is a curve, right? But in a two-dimensional plane like this, the graph is going up, going down, and all that, right? But now when we add in, when we have a third dimension that's coming out like that, right? Then the graph becomes, the graph no longer is a curve like this anymore, not a flat curve on a flat plane like that anymore, but it becomes sort of like a surface. Okay? Like say, you see this border line right here is only a surface. Being flat or being bent, it's a surface. Okay? It contains a lot of points like that, right? And then now it has its projection on this floor, it has its own projection on the wall, on the two walls again. You know what I'm saying? No? So the graph, when we make that transition from a 2D graph, right, to a 3D graph, the curves becomes surfaces, right, or the plane, okay. And so in that way, let me kind of draw the best I can do right now. But think about now when we're having a 3D graph, right? In your account 4, you will see a lot of this. Like say something like this. Kind of like an umbrella, right? That covering the X, Y, 4. And so we can take a sort of like a slice through. You guys imagine what I'm trying to draw right there? We can take a slice through right there. And that here right there is one point on its own. It has its projection on that floor because this plane right now is parallel with the X, Z plane. See that there? And the same thing, we can also take another slice right through this, right? And creating a different plane right here. Okay? And that plane here is now parallel with the with the YZ YZ wall. Okay? And so now let me just create a couple examples where you guys get your skills comfortable with recognizing these projections with them. Alright, so let's look at example 1. And we're trying to sketch, but let's just do the best we can. That's all. So sketch the surface in R3. Okay. Represented by. Alright, so the first surface I want to sketch in R3. Okay, so we got three variables named right here, the X, Y, and Z. Why don't you guys pick only one among the three letters? X, Y, and Z, pick one. Just pick one. Z? Okay, Z. Okay, pick a number. 3. Okay. Z equals 3. So how do I see this in R3 space right here? So I'm going to draw a version like this, where these are the negative sides, right? Negative sides are here, and negative sides is down here, positive z, okay? On the x, on the y. Sounds good? So when it says z equals 3, that means, hey, this R3 space has infinitely many points, right? But all of these points that satisfies this, I want z equals 3. Am I making sense? Out of all points, we're not going to take all points, we take only those points where the z coordinates equals 3. So right here, tackle down right on the z-axis. About 3, 1, 2, 3, about there, right? Z coordinates equals 3. So you got that point right there. But now it's not just one singular point, right? It's the whole plane parallel with the, you see, my drawing skill has reached its limitation. Forgive me on that, guys. But we have a whole plane with that. The plane is supposed to be parallel with the x, y coordinate here. So it's a plane, okay? Parallel to the x, y plane. Right? And then intersecting the z-axis, right? At z equals 3. That's it. And of course, please don't misjudge my drawing, okay? An idea with that so far? So think about it on your own time at home. You can think about, hey, if I give you sort of like an FYT for you to think about, right? Let's say y equals -2, for example. What graph do you imagine in mind? Y equals -2, for example. So have to be, see, on the y-axis, right? On the y-axis, be negative. Somewhere on the y-axis, right? We're going to have a fall, and we're going to have a wall that's going right through that, right? But parallel with the x and z axis this time. The x z plane, that's something that's that right there. -2, make a label. Y equals -2 right there in the spot. That's what you think about. It's all about, we take the idea of the projection. Ready for another problem in this same example? So, part B here. Once again, out of the 3 letters, x, y, and z, you pick 2 for me this time. Pick 2 for me. Pick 2 letters out of the x, y, z. Y and z. Okay, pick a number. Anyone? Go ahead, pick a number. 4? Okay. And you said y and z, right? So how about y equals z squared plus 4? Okay. So we have an equation, don't we? Right there we have an equation relating only between x variable and y variable. Now in this day, starting this day right there, right? Any equation, we gotta have the third variable involved, right? It's just not present in this equation, but it's always there in space. See what I'm saying now? So how do I see this? And this is a good example where you see the idea of understanding the projection right here. Okay, so in a x, y, and z graphing space, okay? So this equation, since it only has 2 variables, y and z, right? So it makes perfect sense that we have to work on the y-z plane with you. You guys follow it? We start now working on the y-z plane because the equation itself, you're right at first sight, it caught our attention that it has only 2 variables, but y and z namely. Agree with that? Okay. And so now, see, try to look like this. Because now this is the positive y, right? And either way, how the equation is currently written, it looks like y can be, y is written as a function of z here, right? So we can kind of look like that. The y-axis is here, the vertical axis, right? And then this is the z. The positive z is going this way, so it's a parabola. So on this wall right here, it's going to have to be a parabola. Bottom peak at 4. Agree with me on that? Right on the the YZ plane again. I'm talking about this parabola stay flat. It's a projection, right? And now here's the idea. So if my y-axis is there, it creates the whole shape like this coming out. You guys see that there? So this is the projection on the YZ plane, right? But we have, as a matter of fact, in the real 3D space, it's a whole surface kind of rolled in like that, right? Through a parabolic shape like that, right? Projection is on the YZ floor, but it's coming through, right? It's coming out, it's coming through the wall right there. Does that make sense? Right? That's how you're seeing it. So once again, keep working on your, on these days, you can hop on Google, they have tons of apps that they run through Java or Java applets or something like that do these animations where you guys get comfortable with looking at graphs. So it trains your visualization skills. Okay? And so that's how I'm seeing it. So now, when it comes to drawing, it's giving me such a challenge. So that's why I did the paper thingy earlier. Okay, save me from the drawing. Otherwise, I don't think I'm that good. All right. So now we're done with that particular example. So once again, let's look back in the old days here. For 2Ds, you got a point A with some coordinates XA and YA, right? You got another point here with coordinates, and I call it the point here is point B with coordinates XB, YB. You guys still remember the formula to calculate distance between these 2 points? What's that? So the distance, the actual distance we did. XA minus XB, really square difference, plus YA minus YB. So the subscript A and subscript B is indicated as the Y value for that corresponding point, or the X value for that corresponding point. Okay? So the difference in X values and the difference in Y coordinates, right? The squares are the differences. You add them up, and then inside the square root, that's the distance. Remember that formula? It came out because of the Pythagorean theorem. See, from A to B, we have a change in X coordinates, right? Being, see, this distance right here is that distance right there. Is your XA minus XB, or XB minus XA. Because when we square that, it's going to be all positive anyway, right? Should be. If we're looking from the left to the right, it should be XB minus XA, which shouldn't matter really. And then this distance right here, YB minus YA, changing Y coordinates. That's why we've got these two differences. But now Pythagorean says we square the two because we form into a triangular setup, didn't we? Right? A right triangular setup, right? Where Pythagorean theorem says this is the square of the two legs here, right? Equals the square of the hypotenuse. So the distance here is the hypotenuse. So now, but then Pythagorean theorem says without a square root, it's going to equal d squared like that, right? So to get d, we take the square root. That's how. Right? So that was the old days, right? Everything we know about that, finding the distances in the old days. So now we're moving into the three-dimensional. Right? Now you got a point. You got another point here. Right? Now it's A, XA, YA, and ZA. And there's a point B, X, Y, and Z. Okay. So very similar. I mean, it's just, I don't want to get into the drawing, because it's just the same argument that they're drawing it. It's going to make really such a, you know, a challenge for me up here. So you're going to take the difference in the x coordinates, xa minus xb, square that difference, plus ya minus yb, square the difference, right? Plus za minus zb, square the difference, and take the square root. That's 3 versions again. To get us the length for any length between any 2 points in a unique space. So right from that, right at this point right here, let's look into another example. Okay, one to calculate the distance. From part A, how about 1 point? Let's call that. B2, 7, and Q. Five. Right? Got those 2 points in space. Formula I use xa, xb, and so on. You'll see that just means just means that the x coordinates for the point and the y coordinates for the points, etc., etc., etc. So now when we call these points p and q, then this is how it works. So you find the distance, right? So square root, then the change in x coordinates between these points, right? So it's 2 minus 1. Make sure it's square that, right? Then the change in the y coordinate, so -1 minus -3. Right? Be careful with signs right there. And then the change in aggregate, the change in the z coordinate, so 7 minus -5, and square that. So now we can do the calculation. What's that? Oh, it should be 5, huh? You're right. Thank you for that. And then when it gets to this, you know, let's get comfortable with using square root expression like that. So that's the 1 like that, right? So it's the 1, right? And then plus 4 here, plus the other 4. So it's perfect.
It should be plus 2. Oh, yeah.
Square, right?
Yeah. 2x.
So it's going to be 3 here. Square root of 9 is 3. But if some other problem, it may not turn out as a perfect square, so we leave that. So square root expression like that. Good enough with that example so far? I mean, I have another one for you to have a look at. I believe this stuff is easy, so that's why you may feel that I'm moving a little faster with this. So to calculate the distance between a point like or 1 and x, z, point what's that?
Is that
Yes.
X equals
Yeah.
Oh,
See?
I mean, y equals 0 and x.
Yeah, y equals 0. Because think about it, when you're taking the distance between any point, it's just a matter a little bit about the understanding the structure. You got a point, right? And you want to calculate the distance from that point generally to any of the 3 walls again, right? So that means we're just looking at, that distance has to be right to that projection point here. Okay? So the distance is here. That's the one we calculated. But the point that we're calculating to right there, that's the projection. So what's that experience we've learned about the projection point? If this point here is being projected right onto the the xz plane right here, then the y value has to be, so it's going to be 5, 0, and 1 right there. Okay? Whereas here is a 5, 4, 1. You guys follow with that right there? Okay? So now, let's just lay down the formula, and then later on when you've done this enough, and you will become fast. It will become a lot faster. We just know that the projection point on that particular point here is 0 for the y value. Right? So once again, the distance here, square root, and then we're looking at 5 minus 5 all square plus, now 4 minus 0, right? All square, agree? Right? Plus, and then 1 minus 1 all square. You see anything nice about that? It's going to zero out the rocks, right? It's going to have a rock, zero out. Forget it. So now it's going to become just simply square root of 16 here. Because that one's gone, only that becomes a 4 squared, right? Which is a 16 next to the square root, that gives me a 4 there. You see what's special about that? It's just really, that space right here is just exactly the y value that was missing right there when we take that onto that projection point. So yes, that's formally how we do the calculation, but trust me, one day when you guys are fast enough, I don't recommend going fast tricks or anything like that, but eventually when you will grow maturity enough and you do this, we'll get there when you guys become very fast at doing this. Okay. Alright, so we're good with that example. And so just like that, just now we learned about the formula to calculate length or any distance between any 2 points. Then, again, back in the old days, where we're looking at 2D things. Okay, point right here, and then there's a tracer. There's a graph going right around it. What do we call this thing? I'm not drawing the best picture of that, but what do we call that shape right here? It's a circle, right? And then it got center. So for us now, since we learned about graphs, any point has coordinates. So the center C right here, XC and YC, you guys agree? Right? But one famous property about the circle is that it's a trace of all these points when making a fixed distance from the center. Okay? That's why, whether you're here or you're there, that's why it's called a radius, right? It's a fixed distance. Okay? The trace of points that make a fixed distance, that's the formal definition of a circle. And that fixed distance, we name that the radius. Okay? And so radius is a distance. So that's why we usually know this formula for any equation. X, because any point on this circle is generally represented by a point x comma y, right? So x, y is just a point on the circle, but now x subtract xc here, the x coordinates for the center, like that, square, plus the difference between any point, any y value on the circle, minus the y value of the center, right? Square, that's the difference, it equals to r squared. The radius squares. It's the distance formula again, but we square both sides of that. Because the distance here is basically it's the distance between any point on the circle back to that center again, right? And since the circle already has a given center, and we have the r value here as being a constant, right? It's a constant here, and then it becomes that famous equation for any circle. Back in the old days, we were learning about the equation of circle. I believe the pre-calculus 1 students or should be fluent with us, and then we keep doing that on, right, into our calculus understanding. Any questions on that? So that's a 2D flat version. Right? enough, you reminder? And so now, when we take that idea right there, right, and bring that into a 3D space, a circle now become a sphere, right? There's a center, and things going perfectly around it, going perfectly around it like a ball, right? And yes, some textbooks they call it a three-dimensional ball right there. So a circle is a two-dimensional ball, and a sphere is a three-dimensional ball right there. Okay, so you got a ball. I don't like my drawing skill today. Just not doing the job well. Okay? So from that center over here, it makes a fixed distance, right, out to the surface of the sphere like that. So, and that center over here, let's name it. Let's call it point C with coordinates XC, YC, ZC, right? So, with that point right there, that description of this sphere that we're looking at, then our equation becomes so just exactly that version. We extend that to one more dimension. So any x point on the sphere itself, right? Any point on the sphere is represented by a triplet, x, y, and z. Okay? And so making the distance back to that point with that. That's why we're looking at x minus xc squared plus y minus yc squared, right? Plus now z minus vc squared. And the square of those three differences equals to the square of the radius. Right? We've got the famous equation of a circle. I mean, not the circle, it's the equation of a sphere. Okay? It's the equation of a sphere. A three-dimensional ball. Yes.
So which means the floor is on the this is two walls. So if they are between, it's on the middle, right? But on top of the floor, and it's going to be on the middle. If there is a
I'm not sure what you mean by middle, but it's just any ball in
any ball.
Yeah, any ball in space. Yeah. And just like that, any ball, any sphere has to have a center, right? That point right in the middle of the whole sphere itself. And that's what we call the center. And so any point on the surface of the ball here, making the distance back to that, then see any point here is having the represented by the triplets, x, y, and z again. Okay? And then that point here has special coordinates, xc, yc, and zc. Okay? And so we come up with that equation there. Okay? So just to get comfortable with that, let me walk you guys through another example. Let's look at example 3. So just write the equation. Write the equation of a sphere or a ball with radius or equals to v, and center at one, 2, 1. Okay. That's the given information about our sphere, our two-dimensional ball. And so the instruction of this problem is only asking for, to come up with the equation, right? And so that's the way how we structure the equation. And so that means the information about the center is right here. Okay? And so it's going to be just x, meaning any x value, the x value for any points on the surface of the ball. Right? X minus -1, that means we're making it +1, right? So x plus 1 squared plus, and then y, the y value for any point on the ball itself, on the surface of the ball, right? And then -2 squared plus, and then the z coordinates of any point on the surface of the ball, the sphere, and -1 squared. Okay? And then what's the radius? 3, so it equals 9. That's how we're done. Nice and simple. Okay. And if it's not asked for, you don't even have to FOIL out or anything like that. That's already the complete equation for your sphere. Right? So that example is intended to be something simple. All right. There may be another kind of problem. Let me introduce that in a different example here. So we are given an equation that say x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equals 0. Okay? And with that equation, now we want to show that in part A, let's show that this is the equation of a sphere. Okay. So, I mean, boy, at first the equation is looking all over, right? But then the idea here is that as long as we can bring it to the form, to the goal here, as long as we can turn that equation into the form of x minus some xc point, right? Squared and plus with y minus some yc, all squared plus some z minus some zc squared, that equals a constant value. That's what, as long as we can bring that equation into this form right here, and then that's the equation of a circle. Okay? I mean, technically it's a k squared. K squared, I mean, r squared again is just a constant, right? That's why I'm leaving it as a constant right here. Okay? And so now, when it gets into this, to get to that goal right there, all it does here is, all we need to do is take some algebra set. So we started with your equation, x squared plus y squared plus z squared plus 4x, right? Minus 6y plus 2z. And the first thing I'm going to do is I'm going to subtract that 6 to both sides, to the other side. It's just a style of mine. I mean, you don't have to approach it this way. It's just a style of mine to keep things organized. I'm going to bring all the constant terms to the opposite side. Okay? And then in the meanwhile, in my next step, I'm going to see there's a 4x, and there's an x squared, there's a y squared, and there's another y term, right? And there's a z squared, and there's a z term right there. So let's purposely regroup them. So we're looking at x squared plus 4x, okay? And then plus, yes, y squared minus 6y. See what I'm doing there? Okay? Plus, and then we have z squared plus 2z. Okay? Equals -6. So now, yes, at this point, we just like what I've been telling you guys, anytime randomly, you need to get your algebra going, right? You gotta review your algebra over here. Remember those days back in algebra that we learned how to complete a perfect square? Okay, this is almost a perfect square already, right? It just needs one more term here to make that a perfect square or turn it into a trinomial. Okay, and so for the x square plus 4x. What constant do I need here in order to turn that into a perfect square? What constant do I need for that? A 4? Yes, I agree. It's a 4 here. But now here's the thing. So in algebra, if you add a 4, right? You have to add a 4 to the opposite side as well. Right? That's why, right from the beginning, it's just my style. Some people, they do add 4, they subtract 4 here. Okay? And then eventually they're going to bring all constants to the opposite side. For my style, I just bring all constants to the opposite side. So if I add a 4 to that group, I add 1 4 to the opposite side. Sounds good? Okay? So that's already a perfect square right there. What about the next group in the middle? It's a y squared minus 6y right here. So what constant do we need? Nine? Okay. You add 9 here. Sounds good? Okay. And yes, I agree with that. Then the last group right here, you added 1, right? So 1. So now here's how it looks. These are now perfect squares because in your equation, these are all the perfect squares, right? So that's going to give me, for the first group, again, it's x plus 2 all squared. Okay? The middle group, it's going to be y minus 3 all squared. Third group, z plus 1 all squared. And then on the right hand side, see, 4 plus 9, right? So that's making 10 like that. I mean, 9 plus 1 is a 10, that's a 14. Taking 6 away, that's 8. Do you see the equation of a circle? Okay? Yes. And see, this is square root of 8 all squared again. Now that displays the radius information, right? So part B of this example, identify right from that equation that you have arrived there, right? Identify or indicate whatever the center and radius. That should be easy enough, right? Center here, that point, but minus 2, agree? Okay. 3 positive with negative 1. So you've got the coordinates for the center. And then the radius here, I purposely wrote that. So it's 8, right? As the ordinary way how the equation looks, but in the end it's going to be the square root of 8. So 2 square root of 8. I mean 2 square root of 2. Because, well, you guys know enough algebra that square root of 8 is 2 square root of 2, right? Okay. There you go. All right. Got the radius. Yes, go ahead and review your algebra if you feel shaky at any point when I was going through this example.